honored to have the only geologist that has walked on the moon and corrects us when we misrepresent his data and the samples that he brought back. Jack is remarkable in that this is the 45th anniversary of Apollo 17, yet he is still highly interested in the samples and the data that were acquired. He's still publishing papers. He is still giving scientific presentations. He is still exceedingly relevant in the debate of the origin and evolution of the moon and getting us back there. So, I mean, I've referred to Jack before as a national treasure. I would say he's an international treasure. We are deeply honored to have him here to talk to us, to tell us about how the last Apollo samples were collected and some of the insights that he has gleaned over the years. And I just give you Harrison H. Schmitt, Apollo 17 astronaut and the only geologist to walk on the moon.
Well, thank you very much. It's, as usual, a great pleasure to be here with you. Thank you, Jim. Appreciate it. Oh, come on. Unnecessary. Thank you. I'll accept that on the thousands of colleagues that made it all possible. And believe me, as I've said many times and others have said, we were just the tip of the spear. And it was being held by a whole bunch of other people. One hell of a tip, though, Jack. little risk involved there, but not much. And I'm going to go very quickly, hopefully not too dryly, through the sample collections of Apollo 17. That should work. There we go. I don't want to go that far. You all are familiar with this planetary body. I still think of it as a small planet and a home away from home at times. The Apollo 17 plan is basically what we did. These are the stations that we occupied and had a chance to examine a whole variety of in situ as well as transported materials that really are still telling us a great deal today. Far too often, I guess I say it's the gift that keeps on giving. That's been the implication of several of the talks today. And that our landing point, which is just at the tip of the arrow, and as a matter of fact, tells us something about the lunar regolith, in that each of the landing points have an area of white or of lighter colored material around them, almost certainly produced by the winnowing of the darker fine-grained material away from the point of landing. And when you saw some of the earlier pictures, you could see footprints in that area. It is very difficult to find them away from that area. And the footprints, of course, are because we have stirred up the darker material still remaining underneath the landing point. And there you see what I was referring to, and a very tortuous path out to the offset site. Until I saw this picture, I didn't realize it was that tortuous. And I actually went much farther than I needed to. As you can see, there would have been a great deployment area. Figure out how to operate this right there, right in that area. But I had to go out here and got one that worked, but probably was not quite as good. The first station, geological station, of course, we were collecting around the lunar module all the time. And that's why I have the samples. Of course, the 7-0 samples were all collected in the vicinity of the lunar module. And we may talk about one or two of those a little bit more later. But the first real geological station was Station 1. It is in a, now we know, and as NOAA has been working out, in a cluster of probably contemporaneous impacts, craters, that have excavated probably one specific flow, maybe two, based on the analysis that I've been able to do. And maybe the most important of those samples was the rake sample. Now, I keep telling people that we should have called it a sieve sample, and Brad talks about a sieve, and there's a lesson in this as well as in all the sieve samples. This one, of course, the rake samples was a construct, a tool that we hoped would sample a wide variety of rocks thrown in from other areas. Well, in this particular case, all we got were basalt fragments, I think 59. And when you do some analysis, compositional analysis, some trends in them, as I have done, they basically, except for 4, probably came from the same flow. And they do give you a crystallization history of that flow, which is, I think, important to know. We sort of guessed at some of it from Apollo 12. As you recall, we had ginger ale bottle glass around the craters that were visited by Pete and Al on that mission. Turned out, of course, to be olivine, and I suspect each one of these flows, because of the low viscosity of the flow, each one of them has an almost monomineralic layer of olivine at the base, and maybe an ilmenite layer on top of it where you had high titanium basalts like we had in Apollo 17. But these are extraordinary, I think, useful samples. As I'll mention in a moment, we got some brand new information from 2 of them. Now, the boulder one at Station 2 that Dave has gotten very interested in now, fortunately, it's time for another consortium, and he'll talk about that more at LPSC. That is the most complex boulder that we visited. All the others seem to be combinations of 1 or 2 melt breccias, fairly uniform in character, as you'll see. This one was, obviously, I think I use the term foliated, being an old metamorphic petrologist, and we tried to sample across it, at least I tried to get it sampled across it, and I think we did fairly well. And if you just look at some of the reported ages, they go all across the spectrum. And so it is time to not only revisit that previous work, but to try to get some new, much higher precision age dating done on this. This boulder may turn out to be an aggregate of ejecta from a whole bunch of basins. How it came about, I'm not sure I can tell you, but it certainly is heterogeneous and something I think can tell us a great deal about Hadean period on the moon that I mentioned earlier. One of the most interesting to me, of course, is that it's what's in red up here is this zircon date of 4.33 that seems to correlate with Lars Borg's work on the MG suite, where he's starting to see a concentration of ages in that time frame. And I think even he is starting to move towards the possibility that Procolarum actually is an impact basin. This is the next boulder we looked at, boulder 2. Very uniform in character. I was fooled for a while, something to remember, that I can be fooled. There was a spall on this that exposed a lighter color. You can't see it in the photographs nearly as well as you could see it in place, but there was a spall. I thought it was an inclusion of another melt breccia. It took me about 10 or 15 minutes to finally realize that we were sampling the same rock and got more samples than we probably needed, used up time we probably shouldn't have at this point, just because I was fooled by that spall. The boulder 3 at Station 2 turned about to be the one with the fragment of dunite in it. And this is a fragment that now looks to be possibly has come from the mantle of the moon due to some other process that I won't go into right now, but have at other occasions. It also gave us another melt breccia, 435, and gave us a sample of regolith that I really haven't looked at again to see what it might tell us, but we got both outside and underneath that boulder because the boulder was small enough that we could roll it and get it out of the way. Going across the light mantle avalanche deposit, We did a number of samples, but one in particular was that avalanche deposit visually was covered, pockmarked by these little bright craters, like this one in this photograph, brighter again to the eye than appears in the photograph. And so I had Gene stop, and I took some samples from inside that, and samples outside as well. Part of the whole Regolith story, which is yet to be consummated, believe me, we have so many Regolith samples in the Apollo 17 site that there's a whole new, maybe consortium that ought to be put together to just deal with the Regolith. The Regolith that's developed on the light mantle probably is developed only over about the last 75 to 100 million years. It depends on whether you use crater frequency or exposure age dates for that. But at a relatively short time ago, this regolith developed about my estimate was about 5 centimeters thick, based on the color change below that level. The surface became, or the material became much lighter. This is down at Station 3. I dug a trench on the rim of a crater. I'm not quite exactly sure why I did that, other than it seemed appropriate. Having thought about impact craters prior to this, sometimes you can get a distended layering of the material that the impact has penetrated. And indeed, we got a wide variety of material in the rim of this crater. Ryan and I have talked about whether or not one of these samples actually has been misdated in the collection, because the way, and I believe it's the darker one seems to have an exposure age that would suggest that it's older than it's mentioned in the catalogs. But nevertheless, again, this is part of the whole Regolith story, and it's probably part of the whole light mantle avalanche story as well. We also collected at this point quite a number of fragments, which really are South Massif fragments, and I think need to be evaluated in that context. And in our recent Icarus paper, I think I made the boo-boo, now I know, of saying that there's no scar from that avalanche on the South Massif. And up to that time, I had not seen one. Mark Robinson just sent me some beautiful, very high oblique, but still nearly zero phase LRO photographs of the South Massif, and believe me, there's a scar. It's an albedo scar, and it is really quite striking. Hopefully at some point you'll have a chance to see those images. Now, at Station 3, we also got a 70 centimeter deep core. The lower half of that is one of the cores that has not been opened and presumably is still in cold storage. Ryan? Not kept cold. Oh, too bad. Anyway, that's one of them. And one thing I want to point out, though, and there's been a little bit of talk about the lobate ridges, lobate scarps, and that's just, you can see where we were relative to the edge of one of those lobes on this. But I'm fairly well convinced now that those lobes are the result of actually these thrust faults moving above the surface and then collapsing. And the lobes of the collapse are not the line of the fault itself. The line of the fault itself is to the left in this picture, probably about 500 meters. And with the LRO photography, you can actually make an estimate from that distance what the dip of these faults are. We had two ways to check that in the Apollo 17. One is because it follows contours on the North Massif, and then this business of these the collapse of these lobes, and it looks like it's about a 26-degree dip. So they're very low-angle thrust faults, and I think this kind of information now can lead us further in analyzing other of the many lobate scarps that exist on the moon. Now, a Shorty crater, we talked about at LPSC last year quite extensively. Really one of the more exciting craters. And now all I will say with respect to sampling is that I think we covered those samples this site pretty well in the half hour that we had. The only samples that I regret not being able to get are right at the edge here, the contact with the light-colored regolith that's protected this material over 3.5 billion years. That orange color becomes much more yellow, obviously yellow, when you look at it, particularly in zero phase. You have to realize that none of the photographs, unfortunately, are zero phase photographs. And this was much brighter in zero phase because it's a beaded reflector. And so you got a much stronger color perception with your eye and brain than you can get with the photographs that we actually took. The core, 74001/2, was taken approximately in that position. It immediately exposed just below the depth that I dug that the so-called orange soil was really mostly black and black ash, and a layered black ash, as near as we can tell from, as I can tell from the descriptions that were made early on, and there are exposure ages for those layers, and all of this, including the dating of the orange soil and the bottom of the core, I think they're both uranium lead dates, indicate that these eruptions took place over about 150 million years. Now, that's not real unusual here on Earth, but I'm not sure that we really had been thinking about that length of time of eruptions taking place on the moon. But there's no reason not to think that that might not be the case, and we should continue to explore that. Now, the Camelot crater, Station 5, at the time, our mistaken analysis, I think, was that it was a relatively young crater because we saw boulders at its rim on the pre-mission photography, Apollo 15 photography that we were using for planning and navigation purposes. However, when we got there, that's the only place there were boulders. There are no boulders on the ejecta blanket. And so that immediately makes you think that, hey, it's older than we thought by quite a bit. And in fact, Caleb Fassett has done a topographic exposure, or topographic diffusion age across it, and he comes up with a 500 to 800 million years, as I recall. So it's an old crater. And and then how do you explain these boulders at the edge? They're probably wall rock. They're probably being exposed as the crater erodes and diffuses downward. And that has led us then to get Ben Weiss involved, and he's going to have a paper at LPSC, or his student is, that of a sample off of 7055, which I hope you can see there. Oops. Right, I'm having trouble with this one. There you go. This boulder right there that we've now oriented in space, and on the assumption it's wall rock, we're just rotating it down so that we not only have a horizontal, but we know the azimuth to the center of the crater. So we're going to be able to get a paleo orientation of the magnetic field at that time from that sample. And there's one other sample, 75075, that isn't in this picture, where it is in situ sample. We can do the same thing. That one's from a crack in a flat rock, and that's the reason I sampled it. Was I knew it was in situ and could bring it out, and the rock's already a big rock, horizontal, and probably hasn't rotated upward at all. So we're going to gain some information, and he'll have a paper at LPSC that I think will give you the idea of whether there was a global field at this time. Just another thing. This is how we, Ron Wells, working with Ben and myself, has actually identified where these boulders are on the rim of the crater using the high-resolution LRO photograph that NOAA made available to us just a couple weeks ago. There's that sample that now we're working with, and hopefully at LPSC we'll have definitive measurement of a paleo direction of the magnetic field at about 3.7 GA plus or minus 0.1. The lunar basalt's ages are a real puzzle. They go all the way from 3.8 8 something to 3.6, and it seems like they vary across isotopic systems, and it's just one of the, again, a consortium of work on the age dating of lunar basalts, particularly Apollo 17 would be quite helpful. And one way that we orient this is that not only is there a planar feature in the rock itself that you see here, and we can follow that around the edge of the rock so we actually can get the orientation, but the top of the boulder was the same way. It had broken along one of these planar vesicle-rich zones. Now, over at Station 6, this big boulder had been identified on the pre-mission photography as having almost certainly rolled down the side of the North Massif, and it was a target. Not all the boulders could be identified on those pre-mission photographs. And when we got there, started to work on it, it was pretty clear that part of the boulder was highly vesicular. Some of these vesicular are 10 centimeters. The vesicles are 10 centimeters in average diameter. One of them actually showed a patina disappearing down into it, which gives you an idea of how those glassy patinas may be developing on the various boulder faces. But the other part of it was much more blue-gray compared to a tan-gray, and they were separated by what was clearly a vesicular contact zone. Now, whether that vesicular and the age dates, I think I have them both up here, are close enough right now within the limits of error to be the same. So those, and we're interpreting those for other reasons. You can read about it in our Icarus paper as being, this being a Crisium melt breccia. Whether that vesicular component is younger, and clearly it's younger because of the metamorphic zone that I could see, but was it intrusive or extrusive? We don't know. But one of the ways in which we might test that is by getting the magnetic orientation of the samples from that boulder and compare it with what we get at Station 5. So there are a whole bunch of things starting to come together because of this gift that we have, and that's the lunar samples. I can't emphasize that more. Now, down at Station 7, I ran into the same thing, and there even the vesicles are a little more obvious. But here, much younger age date, and that's outside the statistical limits of error, even for these kind of analyses. And so we're interpreting that as serenitatis, and that we have, and that boulder, its boulder track leads to a position well above the boulder track from the boulder at Station 6. So it's starting to piece together that we have at least sampled two different melt breccias, melt breccias of two different ages, but that we also may well be able to get some new information, paleomagnetic information, from both of them. Now, at Station 6 also did one of the rake samples, and the reason I bring that up is that we also did one at Station 2. And Station 2 is a regolith that's developed post-avalanche, so it's brand new stuff, so to speak. This is brand old stuff. And when you compare the two, they're very different. And as I talked to last year in this very room, mentioned that I think we've now identified some material that actually has come from a lithic pyroclastic eruptive period that preceded the Maria. And that's something that's always bothered me ever since I flew over the far side of the moon and looked down at some of these large craters, small basins, and they're flat-floored and light-colored, and they have rimless craters in them. So I think, and one thing that, Brad, we're going to have to worry about at South Pole Aiken is whether, at least near those Mare regions, whether or not we have some lithic pyroclastics that preceded those Mares, and we'll have to see if we can identify them. But I'm really, as I indicated earlier, our last year here, pretty excited about this, now seeing in the samples evidence of what has bothered me for 45 years, and that is that what preceded the Mare. And something had to, because as soon as you partially melt something, the volatiles are going to come off first. And they're going to move through the crust and erupt. And maybe that's part, at least, of the Cayley Formation. And I think we see evidence now, or I can see evidence now in the cores at Apollo 16 that we may have sampled that at Apollo 16 as well. So it's going to be fun to keep pursuing that one. Just to show you that these are the pre-rake and the post-rake, you can see the tines there, traces of the tines, I think, in the right-hand picture. Those two rocks are the same rocks. Now, over at Station 8, this was in the Sculptured Hills. It was a planned stop. All of them were. We had hoped to find some more, a lot of boulders coming off the Sculptured Hills. This is the only one that was even almost visible. We could see some way up on some of the peaks, some of the, not peaks, but hills. And so immediately went to work on this. Turns out, and it was obvious right from the beginning, very coarse grain, norite. I could identify twinning on the plagioclase, and it was clearly a hyperscene. I grew up with hyperscene in Norway, and so being a norite was very clear. But I didn't really, it's covered with glass, so where did this stupid thing come from? And you just didn't know. Well, after M-Cube came in, and we started to look at that and start to really think about the Sculptured Hills, I think this is a fragment of the norites in the Sculptured Hills. And it's been, Noah thinks he might have identified a choice of craters from which it came. And so at least we have one sample of that. And when you look at the M-Cube data and extrapolate, now, as we've said in the Icarus paper, it looks like that the Sculptured Hills, at least, are a MG suite pluton that's been thrown in there from Imbrium. It's broken up, but it's still more or less in place relative to its impact history, and exactly where it came from in Imbrium is another thing. But it gives you some idea of how deep Imbrium has penetrated into the lower crust in order to pick up one of these very coarse-grained MG suite plutons, or at least part of one. Also at Station 8, I dug this trench about 30 meters away from an impact crater, and I thought I might be outside the ejecta blanket, the main ejecta blanket of that small impact crater. But when you can see where that's the pre-sampling trench, half trench, and over on the right is the post-sampling. You can see where I just went up the side of the trench and took a series of samples, and when we looked at the maturity ages of those samples, they were upside down, what you would have expected. So it may be we actually were on the ejecta blanket, and that's the reverse ejecta of an impact. This is Station 9, Van Serg crater. And by the way, Anthony, that was great to bring mining geology into the science of the moon. You did an excellent job on that. I've been trying to get people to talk resource science for a long time. But Van Serg was named after the pseudonym of Hugh McKinstry, one of the great mining geologists of the past. That's neither here nor there, except that's why we call it Van Serg. He wrote some great papers if you want to see them. And Noah, I think, has all the references now. One of them is Geologies, How to Confuse Your Reader. And the other is Mathmanship, How to Confuse Your Reader. If you put a footnote in, it's really a power function, things like that. Anyway, I walked up to this, and the surface around the impact crater, obviously fairly young, had these concentration of impact breccias. And we sampled a bunch of them. But you look down in the crater, and again, these photographs can't bring out what the eye can. But these were big boulders, light-colored boulders down in the crater. And I've continued to think that there probably was a thin lava cover on this, but I think it was a lava cover on a knob of Sculptured Hills material. And we did sample one fragment, this 79215, that little white fragment you see there, which is another troctolite, very similar to the troctolite 76535 that was part of the rake sample at Station 6. And except that this one has been recrystallized to the point of where it has a different crystal matrix and does not have the symplectites in it that the 76535 has, that indicate it may have come from the mantle. Now, one sample that I planned to get before we left the Earth was a impact glass sample. The other crews had reported seeing glass puddles, if you will. They're not real puddles, but in fresh craters. And I thought, well, if I can sample one of those and get its orientation, we can at least find out if the lunar magnetic field has progressed on into the near present. And so I kept looking for such a crater, and there's one not far from the limb. And on the last EVA coming back from the, on the second EVA, I believe it was, coming back from the ALSEP after doing some things over there, I stopped, didn't have the gnomon with me, but I took a bunch of pictures, stereo pairs of one of these samples, took the sample, and Ron Wells, again, was able to identify its orientation. He has a new program that you don't need a gnomon anymore if you've got a lot of shadows, enables you to orient all the things, and he's going to give a paper on that at LPSC, I hope, as well, at least the abstract's in. and this was the first sample that we talked Ben Weiss into looking at. He already had some pieces of it, but he didn't realize that we had all this orientation data. And so now he's got another grad students working, I believe a grad student or a postdoc working on this sample to try to see if there is a paleo orientation that can be derived from it. My understanding is probably not, but it does have does have some magnetic intensity. That was reported a long time ago, and so there's a question there of why does it have that? But it may not have an orientation that you might have expected if this glass had cooled in a magnetic field. And this is one of the 215 samples, a very small fragment that NASA brought to the signing ceremony, and I'm explaining in this picture how big that sample was compared to the one that we had to show the president. And that's a lesson, Jim. We should have had a bigger rock. Thank you very much, and if there are any questions, I'd be happy to try to answer. Ivanka was very interested in that, believe me.
Questions for Jack? He's answered it all. Are you going to take that? All right. There's Josh.
I guess so.
There we go.
So I have a question I've always wondered about, since this workshop is partly about landing site selection. There were several sites that were identified for Apollo 18, 19, and 20. And I'm curious, knowing what we know now, whether those were the right sites or not. In other words, if we could do it today, would we go to those sites, or do we have different priorities now?
Well, if we could do it today, I think we had a pretty good selection of Apollo sites. And I repeat again, as I mentioned to somebody earlier, site selection was an iterative process, and there was never any formal site selected until the previous mission results were at least known in a preliminary way. So you had each mission had a number of sites that people were considering for that mission. And so, but the final selection was not complete. And Apollo 17's landing site was particularly late in getting chosen, not because it didn't seem like an ideal place for to put a field geologist because of the three-dimensional aspects of the site, but because had we followed the normal procedure that had been done on Apollo 16 and 15, the error ellipse, 2 sigma error ellipse, 3 sigma error ellipse we were using, very conservative, would have included part of the North Massif in the landing. And with that information, it was still of such great interest that the Belcom people in Washington and the mission plan and analysis people in Flight Control Division at JSC got together and figured out a new way of updating the lunar module state vector 1 orbit later than normal, and that by doing so, that shrunk that ellipse down to about 1 kilometer in radius and fit into the valley. So you can see how the operational and engineering side really played very directly into us being able to get the science that we have obtained so far from Apollo 17 from Taurus Littrow.
Jack, one thing that we've been talking about a lot today is sampling and taking core samples and doing a lot of things automated. I wonder if you could talk about any challenges you faced when you actually physically were sampling from the boulders or drilling or taking cores in the regolith or things like that. If you could talk to challenges you faced.
Well, almost all of the sampling of everything, rocks and soil, was fairly straightforward. It really helped to have your buddy there to hold the bag, to fill it. I mean, that makes a lot of, I tried what we call solo sampling at Station 3, and it was a mess. Anybody who looks at that film and knows that it got to be a mess. And at the same time, the commander was putting that 70-centimeter core into the ground. And it really works better and much more efficient if you have if you use the buddy system. And we knew that. It's just that things were getting tight, and Mission Control recommended that we do we separate and do it separately. But the big challenge, and I talked about this at the league meeting last fall, is in drilling. And we really still don't know how to drill into the lunar surface. It's a highly fragmental. But about half of it is dust, and the other half are larger fragments. It's closest packed. We finally figured out how to get a reasonable core sample by enlarging the sample and making the walls of the core cylinders much thinner than we had before. And we could, not easily, but we could pound those 70-centimeter cores into the surface. I remember watching and commenting at Station 4 when we were doing that core that each whack, Cernan had a bigger hand and he could hold the the hammer better. Each whack he was getting about 1 centimeter near the end. So it's not easy. The rotary percussion drill worked very well going into the surface, but pulling it out, I think what's happens is that the larger fragments rotate into the flutes. And since it's incompressible down there, you can't move that fragment out of the way, and without an extraordinary amount of effort. On Apollo 15, Dave Scott actually wrenched his shoulder doing it. On Apollo 17, you saw some of the effects if you looked at the films of me trying to help get that out. And we finally, on 17, we had a jack, actually, other than myself, what was called a treadle in order to jack it. But even then, you could finally force your way force the core out of the hole. And so we got to think about that. Anybody who's thinking about drilling on the moon, I don't think we have those issues settled yet. Whether acoustical drilling is going to work better with a smooth wall hole or what, that's a subject maybe for a whole nother session sometime.
We go to Ben, and then we're going to end up with Jim with the last word.
So you showed the LROC image. You pointed out that you would have picked a closer location for that station had you had that level of imagery beforehand. And I'm just...
Which station? I'm sorry.
There was one where you... the ALSEP. You thought
the ALSEP. Oh, yeah.
So I'm assuming that the ALSEP location that you chose had been pre-chosen, and I'm just...
No. It was, the only constraint was get 100 meters away. I ended up 180. That 80 meters really, I tell you, when you're carrying something like this, and these forearm muscles aren't in shape like they were for the guys that built the space station. You think they are, but they're not. That 80 meters meant a lot. But no, I had you had the kind of resolution that LROC has given us, we would probably have said, you go put the offset there.
And I wonder if there are other examples where you think you could have bought more time by doing things slightly differently, given the higher resolution that we now have.
You know, probably not.
Okay.
I mean, not significantly. I don't think that even having gone into great more detail in examining the sites and the samples and stuff, and now the LROC photography, and some of it in very high resolution, it's hard to come up with a better plan than we had. Now, did I spend too much time at some stations and not enough at others? Yeah, but that's something that happens in real time, and you think you're doing the right thing, and then all of a sudden you get a discovery like Shorty Crater, and you don't have enough walk-back time in order to stay there more than 30 minutes. But still, then you go into a really accelerated sampling mode, and you get almost everything that you can conceive of doing. Now, had we had another half hour, yeah, I would have gone around to the other side of the crater and sampled some obvious, what now we know is dark volcanic ash on the other side of the crater. There's a nice layer that you can see in some of the pictures on the other side of the crater. And I know that the back room and the Mission Control Center thought a great deal about sending us back to Shorty Crater. I assumed right from the beginning they would not do that, and they did not, because that meant that you were going to lose all the other stuff that we might have discovered. And they were at least wise enough not to recommend it, and I didn't have to argue with them.
Did you have some sort of magnetometer with you to?
We did not on our mission.
Yeah, wow.
Let's see, the last magnetometer flew on 15? 15. Yeah. And now, and I can't tell you what, I don't think they had any significant results, did they? Certainly no anomaly there that I'm aware of.
No, they did have a sat.
No, our magnetometers are in the rocks,
Right.
and that's what we're now trying to develop and get information from.
Thank you.
And I think we're going to get it. I think we'll have. My guess is that we'll know that there's not an extant field now. At least not within the last 100,000 years. Glass doesn't last very long on the lunar surface. I don't quite know how long it lasts. I'm guessing about 100,000 years at the most. We may be able to have a 3.7 GA field orientation from Station 5. And if we can finally get into Station 6 and 7, we may have a 3.9 and a 3.8 GA magnetic field orientation. So that's 3 out of one site. And whether there's an opportunity go back into the collection and find other possible samples to orient, like we have now with Apollo 17. I don't know, Ron Wells is a wonder. He can orient anything, as near as I can tell. The other thing, though, that I think and I'll quit here, but you know, I think we found mantle samples. I really do. I think 72415 and 76535, because of the symplectites in those samples, reflect a low pressure, rapid movement of mantle material to lower pressures. And I think we need to go into the MG suite portion of the collection and see if we can't find some more of those kind of samples. And the fact that we're seeing dunites registering around the Procolarum Basin, I think that's a good sign that, in fact, Procolarum did cause these samples to come up within the range of other impacts to be distributed around that basin. And so if you're looking for landing sites to get to actual mantle material, although I don't think that should be the sole criterion, around Procolarum, there are quite a number of places where you see the signs of those Dunites now. Okay?
Thanks very much, Jack.
Thank you.
All right, we're going to